I would like to welcome you all to the second day of the ICESat-2 Hackweek. I am Nicoletta Cristia in the Department of Civil and Environmental Engineering at University of Washington and also at the Science Institute. I hope you had a chance to join a group project yesterday or just contemplate the content of day one. Before we start today, I just want to quickly remind you of the schedule for today. We will start with a tutorial from Ben Smith about ICESat-2 Data, which is going to be a description of the ICESat-2 Data products, where to find information and how to access the data. Then Naomi will inform us about best practices for effective teamwork, which is going to be awesome for our project work and other activities that the Hackweek is involved with. Then we'll take a quick 15-minute break for movement and coffee. Then we will follow with a tutorial about ICESat-2 data access. In this tutorial that's led by Michaela Bick, we will learn about how to access ICESat-2 data using web mapping interfaces and other programmatic methods. And then we'll take a 45-minute lunch break. And then after the lunch break, we will reunite to listen in about object-oriented programming for collaborative development in Python, which is a fun interactive tutorial that's going to be presented by Romina. Then, as usual, we will get back to project hacking time. Please, as a reminder, use Slack if any questions or issues arise, and anything you would like to tell us, or any problems or other questions you might have. And with that, I think I'd like to invite Ben to the microphone. Thank you.
Thanks for that. We'll get started. So let me see if I can share my screen. And there's the one I want to share. So I'm going to take you guys for a tour of the ICESat-2 standard data products with a couple of stops along the way to talk about where it is that you can get these products, what they're for, and where you can go to learn more about the products once you've decided on one that you want to work with. The idea here is to make clear what has already been done, and hopefully it can save some time if people can go and get data that are already processed rather than inventing new algorithms for themselves. There's a lot that's already been done, but it'll also show the way to come up with refinements to these products, to show you the resources that are available that can help you come up with the next best thing that's going to push the process forwards. So the first thing I want to make clear is that ICESat-2 does not on its own produce geophysical products. So ICESat-2 on orbit measures things like the timing of photons that it's transmitted, measures the timing of the pulse it transmits, it measures the timing of the photons it receives, and it measures the position and orientation of the observatory. So these things on their own don't tell you anything about the Earth. Those have to get telemetered down, and then the geometry gets done to convert those timing measurements and orientation measurements into photons, locations, heights, and times. And that's what gets published in the ATLO3 product, which is just a collection of photon timings. So that also doesn't tell you like where the surface of the Earth is or how cloudy it is someplace. We have to apply further algorithms, which we call level 3+ algorithms, to produce geophysical variables. So that might be the surface height underneath the spacecraft. And so that, for example, that would be ATLO6, ATLO7, or ATLO8. And those three different products are generated using algorithms that were designed for different surface types. So O6 is for land ice, O7 is for sea ice, and ATLO8 is for land vegetation and inland water. among other things. So then there are also some value-added products. For example, ATL10 takes the ATL07 heights for sea ice and infers the freeboard of the sea ice. So it subtracts the elevation of the ocean from the elevation of the ice and tells you how high the ice is standing above the ocean. There's the change product, which is ATL11, which combines different land ice measurements into a time series of heights. And then there are gridded products. So 14, 15, 18, 20, 21, and I think the list is growing probably as we speak, all combine data from multiple tracks to produce a map view that you can actually map. So all of these things are trying to make the products more compact and easier to use. And whether that's helpful to you in your own situation is something that you have to sort of decide for yourself and decide which of these products is going to work best. Here's a flow chart because everybody loves flow charts showing how this works. So there's the satellite data in the boxes over here, which are the level 0 and level 1 products. Those turn into ATL03 and into backscatter profiles. And then ATL03 feeds all the other products, except for the atmospheric characteristics product, which is kind of off on its own because it uses a different stream of data from the satellite. And so those produce the along track products, which are in blue. And then the level 3B products are sort of the value added products, which are, for example, the time series of heights in ATL11 and the gridded products for the other disciplines. Just a quick tour of what this looks like. This is the level 2 product for a chunk of the Greenland ice sheet. And it shows a fuzzy cloud of photon elevations. This was taken at night. You can tell because otherwise there would be a bunch of photons above what's apparently the ice sheet surface that would come from the sun. So here we're just getting photons that come from the surface, and there's usually a trail of photons underneath the surface, which is just energy trickling out of the laser after the full pulse is fired. So we would say that the surface is right here. ATL06 then interprets that cloud of photons and fits a line segment every 40 meters. And in the ATL06 world, the height of the center of that line segment tells you how high the surface is, and the slope of that line segment tells you the slope of the surface. So now we've made an interpretation. We've said something about the world, not just something about the timing of something that we received. Now zooming out slightly, ATL11 then reduces the resolution of ATL06 and combines multiple cycles. So now this is a single file of ATL11 telling you how the surface height changed between cycle 3, which was in April of 2019, through cycle 11, which was 2021, middle of 2021 sometime. So you can see that if you decode these different colors, you'd be able to see that the surface dropped and then recovered a little bit of height. There's just a little bit of cycle 11 here. So cycle 10 and then cycle 11. Anyway, ATL11 is able to tell you the time history of elevations for this little chunk. And then by combining data from all of the available ATL11 data, we can make a map of the area. Now this is zoomed out significantly from what I was showing you before, but it shows you Zachariah ice stream in Northeast Greenland, and it shows you the rate of elevation change. So the mean rate of elevation change is up to 5 or 6 meters per year for the duration of the ICESat-2 mission so far. So between each of these steps, the number of data points you get is smaller, and actually the number of variables gets smaller as well, because ATL03 has to tell you everything, and these higher level products tell you what somebody who was generating the products thought you needed to know, which is generally less. So before I get into the specific products, I want to tell you about some general features of ICESat-2 products that I think will be helpful when you start downloading data and looking at what you get, because there are a few things that can be a little bit confusing. So as Tom described yesterday, ICESat-2 produces a total of 6 beams that are organized into 3 pairs. The reason that they're organized into pairs is so that the satellite can define the surface slope underneath it at all times as it flies along. The pairs are separated by 3 kilometers. the beams within each pair are separated by about 90 meters. So these tracks are designated 1, 2, 3 from left to right, going across the satellite. And then within each pair, beam within each pair may be designated as left or right. So you might have pair 1, left beam, pair 1, right beam. And that's summarized as GT1L, so ground track 1 left, all the way to GT3R, ground track 3 right beam. And usually when you open one of the products, you'll see some variation on this that tells you about which, geographically speaking, beam you're talking about. Now these beams there are a strong beam and a weak beam in each of these pairs. And you're not guaranteed that either the left or the right, you're guaranteed that either the left or the right is going to be strong, but you're not guaranteed which one it is, because sometimes the satellite reverses itself. So there's the forward orientation, where the weak beams are on the left, and there's the backward orientation, where the weak beams are on the right. And ICESat-2 switches between these two orientations a couple of times a year to maximize the amount of light that it gets on its solar arrays. So you may look at a file and find that GT1L is strong. You may look at a file and see that GT1R is strong. You can tell if there's a variable that tells you about the spots, or if you look at the orientation of the spacecraft. But in some ways, the easiest thing to look at is the spot number. Spots 1, 3, and 5 are strong. Spots 2, 4, and 6 are weak. So the spot number tells you about which piece of hardware, like which actual chain of receive electronics received the photons you're looking at. And that depends on that's designated by the spot number. A lot of the products are, especially the land ice products, are described both in geographic coordinates, so latitude and longitude, and in along track and across track coordinates. So the along track coordinates are something that's consistent for each ground track. And it's just the distance measured underneath the satellite as it goes around its orbit. So the circumference of the Earth is about 40,000 kilometers, which means that the X along track coordinate starts at 0 at the equator and gets back to the equator at a number of about 40,000. And it passes over Antarctica and Greenland along the way. So here are some ticks along that measurement, but you can see that these are big numbers. So when you look at the along track coordinate, you may see some rather large numbers, and you may see some inconsistent numbers because some of the tracks crossing any one area might be ascending and some of the tracks might be descending. So these are good numbers for looking at measurements relative to the track that you're in. You may not be able to compare them between an ascending track and a descending track. There's also a Y coordinate that gets defined in some of the products, which is just measured in a right-handed coordinate system relative to the along track coordinate. So Y gives you the distance from the reference ground track to the measurement you're looking at. And this can be helpful when you want to put multiple measurements on the same set of coordinates and compare them. So you want to know whether two tracks overlap. You can look at the Y coordinate, and that will tell you if they're measured in the same place relative to the ground track. So it's helpful for comparing tracks from different cycles. So different times ICESat-2 has flown over your target, you might want to look at the Y coordinates. The ICESat-2 granules, so the data files would be way too huge if we just served them in entire orbits or multiple orbits. So we decided somewhat early on to break the world up into chunks to reduce the volume of the products. So ATLO3 and ATLO6, and I think most of the other higher level products are all broken up this way. So they're broken up into geographical chunks. So region 1 is ascending from the equator. Region 2 is ascending across the mid-latitudes. Region 3 is ascending across the lower Arctic, and region 4 goes across the pole. And then the numbers keep counting through the descending tracks, and then again ascending from the South Pole back to the equator. So you can look at most of the file names, and you can see one of these numbers, and it will tell you whether you are in which of these regions you are in, and it can really help narrow down which products you might want to look at. And we'll see that when we get to my tutorial where I'm downloading products from Svalbard, which is right on the boundary between regions 3 and 5 and regions 4. So before we get started on the next part, I want to make sure that you've understood what I've been talking about. I want you to enter an answer to this question in the Slack channel for ICESat-2 prompts. Suppose ICESat-2 project is planning to release a tasty snack food product. What should that be? The word should needs an H. Please enter your answer in Slack and we'll revisit this while everybody's server is getting started before we do the Jupyter tutorial in a minute. Okay. So the next question is where to go to learn about these products. NSIDC has made a set of landing pages for the ICESat-2 products. You can, basically, the way these landing pages work, if you Google the name of the product, that's the first hit you're going to get. So if I Googled NSIDC ATL06, I would very quickly get to the Atlas land ice product. And this has a number of resources that can help me get to the data and can help me get some technical support for this. In particular, the technical references here link me, let's see if we can get to this, link me to the algorithm theoretical basis document and the data dictionary. Now, the algorithm theoretical basis document is a horrible name for anything. It's abbreviated ATBD, which is something you should remember long after you've forgotten the term algorithm theoretical basis document. But it's the detailed description. It's the manual for your stereo that you never read and you just learn to push the buttons. But when something breaks, you need to go back to that manual and figure out, why you can't reset the timer after the power went out. So the ATBD is there to tell you everything that you might need to know about the product and quite a bit more besides. The data dictionary is somewhat more useful, and it's a parameter by parameter description of the product. So I guess here's the technical references support tab on one of these landing pages. The ATBD is down here, the fourth line. The data dictionary is a big PDF. Again, this is for ATL06. It gives you a paragraph-sized description of each of the variables, which I think mostly contain the information you might need to know. The downside of these is that they're generated by computers and not by people. So both the groups within the products and the variables within the groups are listed in alphabetical order. So what you might care about is what the land ice height is, which is called H_LI. But that's the third thing in the file because it comes third in alphabetical order. So once you realize what the logic here is, it might be a little bit less frustrating to look at these things. So now a tour through the products. I've already discussed ATL03, the geolocated photon product. In addition to the actual locations and heights and timings of the photons, it contains geophysical corrections that get used by some of the higher level products, and it contains a lot of instrumental parameters. So this is the product that has everything, and that's its advantage and its disadvantage. So if you download an ATL03, there's a lot of stuff that comes along with the information that you want to use. And that information is useful for somebody, but it's probably most of it is not useful to you. So this is a product that we've worked to make it unnecessary to download it in most cases. There are ways to get around ever having to download an ATL03 granule, and we'll talk about them. I and other people will talk about ways to get around downloading one of these things because it's pretty hard to use. But if you need it, all the information is there. This is an example of everything, well, all the photons that are in ATL03. And actually some modifications have been made to avoid people having to look at all of these. So this shows a transect across the edge of Antarctica. The surface comes down here, and then we're out over the ocean beyond a certain point. This thing right here is an instrumental artifact. It's a calibration pulse that gets edited out of the data that most of you will look at. But there's also photon classifications. So the different surface type specific algorithms classify the data into likely surface, less likely surface, likely noise. And so there's purple here indicating likely surface, and then a bunch of photons that have been marked as noise. When you get out of the ocean algorithm, or the sea ice algorithm, has been used for those. So you can see that there are a lot of photons, some of which probably come from the surface. I guess when we generated this figure, we didn't apply the classification to those as well. But you can see there's also like photons from clouds. Here, there's just a broad band of photons around the ocean surface. Here we have the surface plus some noise. So like I say, there's a lot of photons here, and it's important to be able to segregate out the ones that you actually want to look at. But again, within this mess of photons, there's some really cool stuff. This is an early slide showing bathymetry. So we see land coming down, then the ocean, and out here we can see individual ocean waves. And then underneath the ocean, we can see down and see 25 meters below the ocean, we can see the ocean bottom. So some really cool stuff is in there if you look for it. We can see glacier surfaces. So this is an example of crevasses over Jakobshavn Glacier, if I remember. So again, this is the along track coordinates and the height, and we see a lot of noise photons and then photons that are colored green because they were classified as surface. You can see quite a few details of the crevasse pattern here. And I think if we zoomed in further, we'd be able to see like some pretty clear signs of individual crevasses. So up till this point, we've been not discipline specific. I'm going to take us through the land ice products now, and then we'll move on to the other products after that. So again, ATLO6 takes the ATLO3 photons and fits line segments to those at 40-meter resolution, and they're posted every 20 meters. So we fit a 40-meter segment to the surface. We step along 20 meters, we fit another 40-meter segment. And that means that we get accurate estimates of the surface height and the slopes. We also take the residuals to those segments and use them to calculate some high vertical resolution corrections. So we can correct for some really subtle errors that the instrument can make due to time variable sensitivity and due to what happens when you cut off the transmit pulse or the return pulse from the surface. So this is aimed at getting sub-centimeter level precision. And when we've evaluated it over nice flat surfaces, we do get sub-centimeter level precision. So the things that you might not like about this one is that the 40-meter resolution is great for the interior of ice sheets, but it might be a little bit coarse once you get off into more complex surfaces. So in some cases, 40 meters is too coarse a resolution. The other thing that I've run into with this is that if you have a big area with lots of tracks over it, 40 meters can be kind of a headache. That is a lot of data points when you get near the pole. So we reduce this resolution as we go up to higher level ICESat-2 products. An example of ATLO6, just showing these segments fitting a pretty smooth flat surface. This is a huge amount of vertical exaggeration. So these things start looking like line segments rather than just as sort of a flat fit to the surface. Here's an example of ATLO6 falling on its face because we've presented it with a supraglacial lake. And so ATLO6 finds, ATLO6 finds the strongest signal, which is sometimes the lake bottom and sometimes the lake surface. And so the measurement of where the surface is bounces around. ATLO6 works well when it's got a smooth, flat surface. Things get a little bit unpredictable when you start throwing different kinds of surfaces at it. Now, the next thing up from ATLO6 is ATL11. This combines multiple measurements on the same repeat track. It's again designed for glacier surfaces. And we take all of the small wiggles in the surface that are measured by these different ATLO6s and correct them back to a set of fixed locations. So ATL11 tells you what the ATLO6s agree about on multiple passes over the same surface. So, and it also propagates the errors from that measurement. So it tells you what the errors in the combined collection of ATL06s are. So this is a smaller and easier to use product compared to a bunch of ATL06s. It loses some detail relative to ATL06, and the reduction may not work as well over very complex surfaces. But this is the product that's designed to look at large-scale glacier change where you're not yet ready to go to a map fuse product. So the show-offy thing here is to take a bunch of ATL11 measurements from Greenland and difference them against each other. And then I've done some work to throw away outliers from this. But it lets you make a map with a lot of points that are all clumped onto each other here of surface height change in Greenland from the end of 2018 through the end of 2020. And you can see the summer of 2019, which was particularly horrible with a lot of drawdown around the edges of Greenland. And then the summer of 20 was not quite as bad as that, but the ice sheet still lost a fair amount of mass. Okay, the next thing, the last one for land ice is ATL 14 and 15, which are, ATL 14 is a land ice digital elevation model, and ATL 15 is an elevation change map of Antarctica. So these bring together all the ATL 11 measurements into a coherent map of ice sheet height and ice sheet elevation change. This came out during AGU this year, so it's pretty new. And we're still on release 1, so there's some warts in it, but it's an easy way of getting a broad scale picture of what's happening with the ice sheets. And it has propagated errors, it's time resolved. So this is a picture of Greenland showing the mean rate of elevation change over the mission so far. So you can see all of your favorite glaciers thinning rapidly. And I picked a single point on Jakobshavn. So here in the dark red blob here, we can see the height measured relative to 2020, showing that the glacier was still somewhat stalled out through the middle of 2020, and then it started thinning rapidly again towards the end of 2020. So you can reach into this map and pull out a time series for any point that you're interested in. And we have this for Antarctica, for Greenland, for Svalbard, for Iceland, for the Russian High Arctic, and for the Canadian High Arctic. So this is subsetted to a few specific places. So the next are the sea ice products. I'm going to move a little bit more quickly through these because I don't know them as well. ATL07 is sea ice height. It's the along track product that gives you sea surface and sea ice height and the type. So it tells you whether you're looking at sea ice or a crack in the sea ice that lets you see the ocean. It uses an adaptive length scale rather than the fixed length scale that ATL06 used to help resolve the sea surface in relatively narrow leads. So the idea is that you just collect 150 photons and talk about the statistics of those photons. So you get finer resolution on a brighter surface and coarser resolution on a dimmer surface. The only disadvantages that I know about this is that it's not calculated everywhere. It's only calculated where the sea ice concentration is thought to be greater than 15%, and it's calculated not too close to the coasts. And I think that there's some work to improve on this. And I guess some funny, I think this is, I asked somebody on the sea ice group to tell me about disadvantages a year ago at least. And I got back that the sea ice classification is less accurate in summer or on melting sea surfaces. But it's still, I think, a state-of-the-art product. You can get a lot of stuff like the height at high resolution. You can get the photon rate, so telling you about the brightness of the surface. And that lets you distinguish leads in the ice from the actual ice surface. ATL10 then looks at a profile like this and identifies the places where there's open water. So it takes those places where there's open water and essentially grids them to form what the sea surface height is, and then compares that to the height of the ice. So ATL10 is the sea ice freeboard. And if you have the freeboard, then if you know something about the density of the ice, you can calculate the thickness of the ice. So this is the value added product on top of ATLO7. It has most of the advantages and disadvantages of ATLO7, but here's the picture of what this looks like. There's the ATLO7 height. There's a place where they've identified that they're measuring the height of the sea surface. You subtract that and it gives you the freeboard. So ATL10 in a lot of cases is the easier to use product compared to ATLO7. Then there are also the vegetation products. The one that I'm going to talk about is ATLO8. ATLO8 performs some more advanced surface classification tactics that are not available on ATLO3, and also measures the canopy height and the land height and vegetated surfaces. And ATLO8 is calculated everywhere. So if you want to know what the vegetation height is in Antarctica, you can do that. It can do a better job in some complex terrain than ATLO6 because it has these algorithms, and it does a much better job over trees than ATLO6 does. And it's available everywhere, which ATLO6 is not. So there's some really good things about this. This is a good thing to use if you need to detect multiple surfaces or if you're working on land or in trees or complex surfaces. Here's an example of what this looks like. Here's the photon classification that is available on ATLO8 to be applied to ATLO3 photons. And here is the interpretation that's generated based on that. So telling you about how high the trees are and how high the land is. It's when this is working well, it's pretty incredible. And then the last quick thing to talk about are atmospheric products. These are ATLO4 and 09, and I think 09 is the one that you would actually look at, which is calibrated backscatter and atmospheric characteristics. And so what these do is that you hope doesn't get in your way when you're looking at ice surfaces and land surfaces. This is a picture of what this looks like. It gives you backscatter in units of meters to the -1 and steradians to the -1. So it's actually calibrating the returns and trying to correct for the atmospheric attenuation. But it shows all of the clouds that ICESat-2 can detect. It also shows the surface brightness. So I guess we're over the ocean here and we've got some clouds above the ocean. There are probably some cases where you might look at a higher level product and not know why you're not seeing the surface. If you looked at ATLO9, it would show you that there were clouds in the way. And there's a lot of other cool stuff in here, like detection of blowing snow layers, that I think would be really interesting to explore. Okay, so last, there's what you do if you look at the products as they're defined now and find that they don't necessarily work for you. So one of the problems might be that there's just too much trouble to download. There are some strategies that have been put into effect, and we're going to hear more about them later on today, for downloading the standard products efficiently. So Open Altimetry and Slide Rule are two services that can do this in real time. So within a second or two of a web-based request, you get back a geographic subset of the product, and often it's reduced to a number of parameters, a smaller number of parameters that might be the ones you want. NSIDC and ICEPICS together are offering custom parameter subsets, and I think they're moving towards real time to get you fast subsets of the products, or get you, fast access to entire product granules if that's what you want. We'll see this when we go through my tutorial. Slide Rule also offers custom ATLO6-like products on demand. So with a latency of seconds, you can specify you want a finer resolution, you want finer posting, you want different signal classification of input. You can get an ATLO6-like product at the click of a button. So that's a cool tool that Tyler will demonstrate, I think, on Thursday. And then if you need it, ATLO3 and the product ATBDs are there. So you could always hack your own thing together using the standard data products. The one thing to keep in mind is that the calibration and validation for ICESat-2 has happened for the standard products. So if you go back to ATL03 and start doing your own calculations, you're somewhat on your own for validating, for justifying to the people who might review your study why you think that this is as accurate as the standard products. The standard products, there's a citation you can go to that will tell you how theoretically accurate your product is. So it's just one extra step that you might have to deal with. So with that, I've used up about half my time, and I'm going to switch over to the Jupyter Hub. And these slides are going to go up as a PDF in my repository sometime later on today. So I'm going to move to a tutorial that's in, let's navigate to this. Actually, maybe I can take 2 seconds. So first of all, do we have any responses for the tasty ICESat-2 snack product? Has anybody been watching? Yes, okay. So can somebody read me the answers? Okay, now I'll read the answers. So we've got wasabi peas, like the photons, which is excellent. Photons. Frosty lightsabers, which I like. Green M&Ms, of course, knockoff green M&Ms. Clearly to penguin jerky. I'm gonna have to think about that one. Nerds on a rope from Open Altimetry. Is there something called Nerds Rope? That I think is past my time. Fantastic Pho is, all right, yeah. And Ben and Jerry's ice cookie set. Big thumbs up to everybody. We'll have to forward these to Tom to generate the products. And of course, NSIDC will distribute the snacks when the time comes. And Slide Rule will offer a slightly less tasty version of that delivered to your door within seconds. Wow, that's a Nerd's Rope. I was born too early. Okay, so moving over to the tutorial on the hub. I'm going to walk through these slides. I realize that, or through these cells, I realize that maybe not everybody has their hubs spun up right now, but we'll let that happen. Let me take a second for questions before we go any further. Can somebody help me if there are questions in the Slack? Anthony?
I was just going to quickly say, were you expecting us to see a piece of kohlrabi or your Jupyter notebook?
I was expecting you to see my Jupyter notebook.
Okay. It's a beautiful kohlrabi that we're seeing.
Let me quit this. Mabue? Is that Dig? Can you say your name?
Yeah. Hi. I have a question. Are there tool software provided specifically for ICESat-2 products? I mean, like a Snap for Sentinel dataset, for example.
That's a good question. Not quite in the same way. So Sentinel, there are processing algorithms that you can download to your computer.
Okay.
I think the general idea is that in most cases, the products themselves are relatively straightforward to access. So for Sentinel, in particular, reading the data products is kind of an exercise if you started to do it from scratch. I think in most cases, the ICESat-2 products are processed to a somewhat higher level than that. But we will be seeing various tools that people have generated that makes the products look like something once you've downloaded them that's easier to interact with than just the raw HDF5s. Okay. I'm going to stop my share and restart it and hope that this works better.
Can I ask questions?
Yes, please.
Okay, I have a few. The first one, I think the result you showed is look like each individual photon point, right?
In some, so for the low level products, for ATLO3, that was the case. For the higher level products, we've started interpreting the
Right.
collections of photons into higher
Yeah.
level.
So then I don't really understand the footprint. So each photon is just one point. How did you define the footprint? You have, I think yesterday Tom said about 11 meters. I see your slide today is 17 meters.
Okay, so yeah, Tom has a more up-to-date number. So the design spec, I think, was something like 17 meters. The number that we quote when we tell you about a footprint is the circle on the ground that encloses 85% of the energy transmitted by ICESat-2 to the surface. So if you put out an array of detectors and you measured where all the light from the satellite hit the ground before it went back to the satellite, that would define roughly a Gaussian shape.
Mm.
And you could draw a contour on your map of where the energy was coming down. That would enclose 85% of the energy that hit the ground. The diameter of that circle is the footprint of the satellite, or the footprint of the laser. So that's just a measurement of how energy has been transmitted to the ground and how it bounces back and gets back to the satellite.
Okay.
ICESat-2 from each of those footprints on a clear day on a bright surface will get between 4 and 16 photons back. So it will receive a number of photons from that footprint.
So you have location within the footprint for each photon, right?
So we know where we were pointing when we transmitted. And so that we know what spot on the Earth we were pointed at when we transmitted. And then we measure the timing of the photons that come back from
Right.
that spot that we were pointing at.
So you have the location within each footprint, each photon, where it's transmitted back, returned back.
So the photons themselves are tagged, are geolocated at the center of that footprint. Like we don't know where in that footprint they actually came from. So we know where we were pointing, we know what time the photons came back. If you look at the geolocation of the photons, they're not scattered over, we don't say that they were scattered over an 11-meter area. We just say that they all came from the center of that footprint. But in fact, there is some randomness to where the actual photons come from. And that randomness has statistics of like an 11-meter circle. Does that help? I realize this is—
Yeah, because you have all this individual photon. I just couldn't really link this with footprint. I understand what the footprint means, but so when you plot your all this photon dot, and that's associated with a location, that's the location of each of the footprint.
Yes.
So you could have a photon like return back from different location, but as far as within that 17 meters footprint, you label as one location.
Yes, that's right. We don't have any information about where it came from. We just know what those statistics look like.
Okay. All right. That's
statistical thing.
Yeah. I have two more questions. Another one is
Wang, we're gonna probably just keep moving. If you don't mind putting those other questions in the help channel, that'd be great, and we can address them so that we can just stay on time in our.
Okay.
Thank you.
Okay, thank you. Are you guys still enjoying my kohlrabi, or have we moved on to data products?
We see some data products now.
Okay, excellent. And let's see, I had this in. Let me put this in presentation mode. There we go. Okay, so in this tutorial, I'm going to show you sort of the most basic techniques to take ICESat-2 data and figure out what data you want to look at and get it up on screen. And again, because I'm obsessive about ice sheets, I'm going to be showing you the land ice products. A lot of these techniques would apply to sea ice or to vegetation products with some different variable names and some different granule names. So the things that I want to show you are how to get the ICESat-2 granules from NSIDC, how to figure out what granules to download using IcePix. And I'll show you briefly some stuff about photon data access using slide rule right at the end of this. There are almost certainly better ways of doing a lot of these techniques. This is the dead simple way of doing things that you'll see perhaps easier ways to do later on, but this is a fallback. If other things don't work for you, if you don't understand the way other things are working, you can always look at things in a low level way with the techniques that I'm showing you now. So I'm going to step through the tutorial, cell at a time. The packages that I'm importing, I think, are relatively standard packages. We're going to be plotting stuff with matplotlib. Slide rule might be the only sort of non-standard thing that we're downloading. All this stuff is available on the hub, and these are all packages that are straightforward to install in a Conda installation. When I've generated this tutorial, it was with all the plots inline, which means that they're not interactive. If you want to be able to interact with the plots after you make them using the zoom tools, it's a great idea to comment out this matplotlib inline and change to matplotlib widget. And the matplotlib widgets interface enables zooming on plots, and it's a really great way of keeping your data alive when you're looking at it. So here's a non-interactive figure of the area we're going to be looking at. This is Svalbard in the Norwegian high Arctic. We're at 80 degrees north, so we're pretty close to the pole. We're specifically going to be looking at the Austfona ice cap, which I'm sure I'm not pronouncing well, and in particular at the Basin 3 Glacier, clever name, which is a glacier that's been surging since the mid-aughts, I guess. The glacier has started speeding up very much faster, and it started drawing down very quickly. So ice has started dumping out of here more quickly, and the surface has gone down as a result. So the first thing we're going to do is to download the ATL15 map view height change field from NSIDC. This is a reasonably sized file to download. It should download pretty quickly for everybody. I've already got it, so it's not a big deal to get it. Oh, and we have to log into Earth data before we can start downloading anything. And this is just the line that was generated for the Hackweek to use Hackweek credentials to log in. If you were doing this on your own, you would have to use your own credentials instead of this UW Hackweek username. But this will get us past the access barriers around NSIDC. So once we've got that, we can just use wget it's a Unix utility that downloads from a URL to load this onto our machine. I'm putting everything on the hub in /temp, which is a good practice that Scott asked me to encourage all of you to do because it keeps things out of your own directory and it avoids quota issues that might come up otherwise. So this cell has run, which means that we've downloaded the file, and we can look at it using the Rio Xarray package, which has utilities for opening raster data sets. So I open the data set on this line, and then I display the standard view of what that product looks like. What we have is a gridded data sets in a polar stereographic projection. So we have the X and Y coordinates for them. And then we have a number of different variables that are all mapped to these X and Y coordinates. So to get an overview of what we're looking at, I'm going to just calculate the rate of height change. So this is just two different fields in the delta H field divided by the time difference between them. And I've converted the time difference into units of years. So we'll get height change in meters per year. And then the other thing you have to do to be able to visualize stuff in Matplotlib is to calculate the extent of the data set. So tell Matplotlib where the corners of the data set are so it can map them. So if we run that, and I guess I have to run both of these. There we go. If we run that, we get a map of Svalbard showing our particular glacier with the rapid drawdown. All of these are the different ice covered areas in Svalbard. And we're mapping the mean rate of height change for between April of 2019 and the end of 2020. So you can see that there are this area of rapid drawdown. There are a few other glaciers that are flowing fast that are also sucking down their surface height rapidly. Since we're in Matplotlib widget mode, we can click on this and we can zoom in to see the area that we're interested in. So that's just a handy feature. For the published tutorial, I just put in an automatic area that we can zoom in on. That's the same as the previous cell, but it's now just zoomed into a standard area. So the nice thing about this sort of zoom in approach is that you can then query where you zoomed. If I hadn't typed in these limits before, we would be able to query what the limits were. And that's a way of informing the rest of your Python notebook what area of the glacier you're looking at. So let's zoom in. We've just zoomed in, then we can ask Matplotlib where we're zoomed to. And in this case, I calculated the center of the area we're zoomed to and the location just to the left of that. And I'm going to plot the height changes from ATL 15. So in that black star that I showed above, so right here, the surface is going down quickly. For this green star, the surface is going down pretty much not at all. And if you plot those heights versus time, you get 2 time series of surface height. So that's what ATL 15 is good for. Are people basically keeping up with me here? Can I get a quick survey of thumbs up, whether this is working? And can someone on the team tell me how this is working for people?
Yeah, Ben, there's a couple errors with Rasterio that we're just checking in on here on the help thread.
All right. I'll let that happen in parallel with what I'm talking about.
Sounds great. We'll be on it.
Okay. So in this tutorial, we're going to go from the highest level data product down to the lowest level data product. So which turns out to be a more efficient way of doing it than going the other direction. So the next thing to look at is the ATL 11 data that went into producing this ATL 15. So ATL 11 is a long track height data. We'd like to know which particular ATL 11 files informed this ATL 15. So we're going to do a query on the common metadata repository, which is a system that NSIDC and NASA have put together that contains the geolocation of all of the ATL 11 files out there, actually all of the ICESat-2 data products. You can draw a square on a map and ask what went through that square. You can ask on a per product basis. So to do that, we're going to take the corners of this region in polar stereographic. We're going to convert them into latitude and longitude, and then we're going to pass them off to the common metadata repository and ask what granules went through that box. So IcePix has automated this task. We form a query that specifies the product and specifies the corners and specifies the time range. And then when we run that query, it tells us that there are 55 different granules that go through that spot. So we can list some of those granules. This is a list of the first 10 of those. And you can see that there's a file name for each of them. Now, the trick is that not all of those are the files that we want. A bunch of them are region 5 granules that go over the pole. So if we look at a file name here, here's an example of a file name, and here's, everything that goes into that file name. So we've got the track number, the region, the cycle, the repeat track cycles that went into it, the release, and the version. Turns out that a bunch of, like this one is a region 3 granule. So it's an ascending track in the northern hemisphere. We don't want the ones that go over the pole because that's a lot of extra data to download and they just barely touch our region. So I'm going to make a regular expression that parses out these file names and decides which of them to actually download. So we're going to pull apart that file name, find the ones that are in region 3, so just the ascending tracks, and then we're going to download those from NSIDC. So if I hit this, it will start downloading them one at a time. And again, I don't think anything too horrible will happen if everybody does this at once. It's just a couple of minutes not even a couple of minutes. It's a couple of seconds for each of those. And we'll download, I don't know, 15 of them or something. So I'm going to rest my voice for just a second, take a sip of coffee while this goes. Are there any questions that I should be answering while we're downloading?
Are you not downloading 03
So we will not
instead of 05?
So we will not download 03. We're going to get that using slide rule in the very last couple of cells of this tutorial. Okay, so there are all the ATL11s. If we do, we can look at the contents of one of these using H5ls. So H5ls is a command line utility. The exclamation point lets you run command line utilities. And so we see that we've got a structure here that has 3 different pair tracks. So the left, middle, and right pair tracks. And you have to go into those pair tracks to find the actual data that we might want to look at. So here we have corrected surface height, latitude, and longitude, as well as quality summary variables. So next we're going to loop over the ATL11s we downloaded, and we're going to read those into a dictionary, which is just a standard Python way of storing data where all of the fields are grouped together into objects that are one object per granule. So it's an easier way of organizing the data so that it's not sort of sprawled out of your workplace. So we're going to read each of these files. We're going to pull out the variables we're interested in, and we're going to store those in a dictionary that has, for its keys, it has the file name, and then it has all of these fields for each entry in the dictionary. So we'll just do that quickly. And once we've done that, we can plot the ATL11 measurement locations. So it turns out that a CMR query can often get you data that are far outside the box that you've designated. So you've asked for a small area. CMR gives you more data than you asked for, but it does give you definitely the data that you did ask for. So here are all of the data over Svalbard. And I've put the location, the file names in the legend for each of these. And so if we pick one of these out, I like this dusty rose color. So we'll pick, so dusty rose is track 548. You see right here. Let's plot the contents of track 548. Oh, I've got a step here where we zoom in and just plot the ones that go over our region of interest. And again, track 548 in pink just hits the edge of the new crater. So if we pull out one of these, we make an index for subsetting to just the stuff that falls within our polygon. We can plot the surface height as a function of time. So now here we are on the left-hand side of the ice cap, going into the right-hand side where the surface has dropped so distinctly. We can see that there are different repeat measurements that are separated vertically from one another, going from cycle 3 to cycle 10, and then cycle 11 rebounds a little bit from cycle 10. If we just pick a single point out of this, so pick a point that's kind of in the middle of this plot. There we go. We can plot the time series. So here we are from early time to late time, going from higher to lower. So there's the time history of that point. So the next thing we might be interested in is the ATL06 data that went into that ATL11. So once again, we're going to do a CMR query, but this time we're going to specify what track we're interested in. So here I've specified track 548 only. Again, the same latitude and longitude limits. If we run this, we see that there are 26 granules available. And then I'm going to again break up the file names to find the ones that are just in region 3, and I'm going to download those again. So this will take just a sec. I realize that I'm running past 10, but I started a few minutes late, so I hope that that's okay.
Yeah, you're good.
Okay, thank you. So there should just be 13 of these because I'm just asking for one track in one region. Let's take 30 more seconds to download the rest of them. Okay, there we go. So again, we can use H5LS to look at one of these things. And you see that here are all 6 ground tracks. Let's look at ground track 2L, so middle pair left B. We've been looking at the middle pair for all of these files. All the rest of the pairs are still there. So there are about 3 times more data than we've been plotting so far. And again, here is latitude, longitude, and surface height, as well as things like the errors in the surface height. And then there are other groups that give you more detail, like the along track slope of the segments. So once again, we're going to read the ATL06 data into a set of dictionaries. And we're going to find the points that are within our region of interest and save that as another field in each of these dictionaries. And let's plot these on the map. So now I've plotted each of these files, each of the cycles individually from their ATL06s. We can see that there's cycle 1 and cycle 2, which are off to the side. And then where are all the rest of the cycles? There's just one line that represents all the rest of the cycles. So cycle 1 and cycle 2 were not pointed correctly, but if we zoom way in on the rest of the data, we can see that all the other cycles are there. They're just right on top of each other. So they only plot as a single line. So this is ICESat-2 working properly. Cycles 1 and cycle 2 are off on their own. So they're a little bit harder to deal with in a repeat track concept. So let's take a look at what's in the ATL06. The ATL06 is less aggressively filtered than ATL11. So in addition to the good data right near the surface, there are a bunch of blunders in ATL06 which need to be filtered out. But there's a variable called ATL06 quality summary. And when that variable is equal to 0, it indicates that there are no suspected errors in the data. So if we just plot the ones for which the quality summary is 0, we get a pretty nice look at the data. Now our axes are flopped from left to right because we're plotting as a function of a long track coordinate, and we're on an ascending track, so we're going from south to north. So now what was on the right is on the left because of the way we plotted things. But again, you can see the surface drawing down. There's just one thing to be careful of here. Cycle 1 in this case is below all the other cycles, and that's because it was measured off to the side. So again, cycles 1 and cycle 2 are cycles to be wary of because they're not measured in the same place as everything else. Okay, so getting to our last group of data, our ATL03. And if you'll recall, ATL03 is a giant product that you don't download unless you have lots of time to do it. So you definitely don't download ATL03 granules during a tutorial because there's not really enough coffee in the world to drink a coffee while an ATL03 is downloading. There is, but it's not something we want to do. So we're going to use slide rule to do this, and slide rule can do on-the-fly subsetting of ATL03. So can IcePix to some extent can do this, and so can open altimetry, but we're going to use slide rule now. We're going to take the ATL06 granule and we're going to substitute O3 for O6, and that will just get us the same granule in ATL03 form. We're going to specify a polygon for this. We're going to ask for surface type number 3, which is the land ice classifications. And then the rest of this are just variables you need to pass to get a look at all of the photons in the file. So we submit this to slide rule. Slide rule goes and farms out the job to a bunch of different servers and sends us back the ATL03 data. This should happen pretty quickly. Yep. And it returns a pandas geodata frame, which contains the time for, so now each row of this is a photon. It gives us the time, the latitude, the longitude, the along track distance, the RGT. It's a tastefully selected group of variables that you might want to look at. And it has an actual geometry for each of these points, which are handy for plotting locations using the more advanced techniques that you'll see later on. Right now, we're just going to plot photon height and confidence values for one of these sets of data. So here we go. So this is the complete photon cloud with the photon classification. So showing photons classified from little confidence that they are not noise to high confidence that they are not noise. The purple are the higher confidence photons. And there are some buffer photons, which just mean that they're close to a high confidence photon. So if we zoom out, we can pretty clearly see where the surface is, but we also see that there are lots of background photons that are solar background noise. And we're able to plot the ATL06 data on top of the ATL03 data because they're in the same along track coordinate system. So if we just plot the O3s again, we can plot the O6s. I think these points that are floating out in space are because slide rule makes some decisions about which altimetry band to return to you. I think that in the complete ATL03 granule, there would be some more photons that we're not seeing here. But in general, what we're seeing here is that as long as there's decent signal strength, we get an ATL06 measurement, at least most of the time. Okay. So that's what I've got for you. Thanks for following along through a whole lot of material that was come up with presented rather quickly. And I'm available to answer questions on the chat for as long as it takes. So thanks very much, everybody.